Hello, and welcome to this video in which we will review ore deposits. This video is meant to be a high-level overview on the complex topic of ore deposits. We have lots to cover, so let's begin. We will begin this video with a review of plate tectonics, followed by a review on the three main rock types since they are both extremely relevant to ore deposits and ore deposit formation. The Earth is made up of 7 major tectonic plates that are always in motion. You can think of these tectonic plates as the thin layer of ice on top of your soda. The soda represents the melted portion of the inside of the Earth, or the mantle, where the magma lives. Tectonic plates are constantly traveling around on the mantle, even if you can't see or feel them doing so. The plates may move toward each other, forming a convergent margin, move away from each other, forming a divergent margin, or slide past one another, forming a transform plate boundary. We will first look at divergent margins. This happens when tectonic plates move away or diverge from one another. When plates move away from one another, the mantle is exposed and magma will move upward and out onto the surface of the Earth as lava, which cools and makes new crust. Next, we will look at convergent margins. Since the Earth is a sphere where there are tectonic plates moving away from each other in one part of the world, there are plates crashing into one another in another part of the world. When plates of equal density crash into one another, they will buckle or fold, and this is where mountains are built. So when continental crust crashes into continental crust, or oceanic crust collides with oceanic crust, neither will give, so they just buckle and build mountains upward. However, when plates of different densities collide, the heavier plate will sink or subduct underneath the lighter plate, eventually turning the heavier plate back into magma. Oceanic crust is very dense or heavy, so it will sink underneath the lighter continental crust. As it sinks and the plate is melted, magma chambers are created which produce volcanic mountain ranges as the buoyant magma tries to reach the surface. Finally, we will look at a transform plate boundary. Transform plate boundaries occur when two tectonic plates slide past one another. An example of this type of boundary is the San Andreas Fault. Let's continue our discussion with a quick review on the three main rock types. For a more thorough review, please watch the videos which specifically address each of the three rock types, which are available on the Nevada Division of Minerals Open Data site or our YouTube channel. Let's begin the review. The three main rock types are igneous, sedimentary, and metamorphic. An igneous rock forms when hot, molten rock, also known as magma, crystallizes and solidifies or turns to rock. The magma forms deep within the Earth and rises to the surface. There are two types of igneous rocks: intrusive igneous rocks and extrusive igneous rocks. Intrusive igneous rocks form when the magma gets stuck inside the Earth and cools there, forming large crystals that are easily visible with the unaided eye. Extrusive igneous rocks form when magma exits through a volcano or a fissure and cools quickly on the surface of the Earth, which does not give the crystals much of a chance to grow. Therefore, the crystals are either very small or not visible with the unaided eye. Remember, mafic refers to magmas, rocks, and minerals that are heavier in weight and darker in color than felsic magmas, rocks, and minerals. Mafic magmas, rocks, and minerals are heavier in weight because they are made up of heavier elements, and the opposite is true for felsic compositions. Sedimentary rocks are rocks that are formed at the surface of the Earth from pre-existing rocks or from pieces of once living organisms. They often exhibit layering or bedding. The three main groups of sedimentary rocks are as follows. 1. Clastic sedimentary rocks, which are rocks made up of clasts and smaller sediments from other rocks that have been broken down by the process of weathering or erosion, transported and deposited somewhere else, and finally cemented together by burial and compaction and turned to stone. 2. Biochemical, bioclastic, and organic rocks, which are rocks made up of fragments of once living creatures that have been broken down by the process of weathering or erosion and are cemented together by burial and compaction. Organic sedimentary rocks are rocks made from the accumulation of the remains of fossil plant matter. And 3. Chemical sedimentary rocks, which form when mineral constituents in a solution become supersaturated and inorganically precipitate. Metamorphic rocks are rocks that are created by the change in form or metamorphism of an existing rock. Changes include compacting the rock into a smaller and denser form, or by changing the minerals present in the original rock, also known as the protolith. The rock that is changing can be igneous, sedimentary, or even metamorphic. Metamorphic rocks can be classified into two groups, foliated and non-foliated metamorphic rocks. Foliated metamorphic rocks are rocks where the minerals have been aligned due to heat and pressure placed on the rock, which was not uniform in all directions. Foliated rocks exhibit distinct layers with distinct mineral compositions. Non-foliated, as the name may suggest, are rocks that do not exhibit distinct layering because metamorphic pressure was uniform in all directions, or the protolith consisted of minerals that can't align except in zones of intense deformation where the rock is more like toothpaste. Ore deposits form due to magmatic processes, circulating hot aqueous fluids, marine processes, evaporation, and weathering. Understanding tectonics and rock types is critical because ore deposits are related to both. Tectonic setting generally controls the location of mineral deposits and gives rise to favorable conditions for specific deposits to form within. Plate movements create stresses on rock, causing them to break, fold, fault, or shear, generating conduits or pathways for mineralizing fluids or milts to ascend through and mineralize in and around. Tectonic processes can also create environments which trap fluids and subsequently cause elemental enrichment, followed by isolated mineral precipitation. The type of rock the mineralizing fluids or milts move through not only influence how the fluids move, but may also control the chemistry of the fluid, can potentially enrich the fluids through chemical leaching, or initiate chemical reactions causing precipitation of minerals within. Next, let's review some terminology. These are terms you will hear throughout this video. First, what is ore? Ore is a naturally occurring solid material from which a metal or valuable mineral can be extracted for profit. Ore is found in host rock. Host rock is the rock surrounding the ore or the type of rock where mineralization occurs. Metallic ores can be sulfides or oxides. A sulfide mineral is a non-silicate mineral containing sulfur combined with one or more metals, but does not contain oxygen. An oxide mineral is a non-silicate mineral containing oxygen combined with one or more metals. Pyrite is made up of iron and sulfur, FeS2. When pyrite is oxidized, the sulfur is replaced with oxygen, which can result in several minerals, including hematite or Fe2O3. The pH of an ore fluid is a common topic encountered when discussing ore deposits. pH is a scale used to specify how acidic or basic a solution is, and the pH of an ore fluid controls many of the characteristics of an ore deposit, such as mineralogy and host rock alteration. And finally, I just wanted to show a diagram depicting the platinum group elements, or the PGEs, so you are familiar with what they are. PGEs occur in a couple of the ore deposit types we will discuss. Before we submerge ourselves into ore deposits, I want to speak briefly on fluid inclusions. There are many tools scientists use to study ore deposits, including mineralogy, geochemistry, isotope analysis, and petrography, but these topics span about 8 semesters of formal instruction. One tool that is widely used to define the fingerprint of an ore deposit is fluid inclusions. What is a fluid inclusion, you ask? A fluid inclusion is a small to microscopic bubble of liquid and gas that gets trapped within a crystal as it is forming. Fluid inclusions preserve the record of the composition of the fluids along with the temperature and pressure of the mineralizing environment. So when we speak of the chemistry, temperature, and depth at which these ore deposits formed, it is likely that fluid inclusions were the source or part of the source of such data. The classification of ore deposits. I would like to start out with saying that ore deposits are complex. This will be a high-level overview of the basic mineral deposit types and common characteristics of each. Ore deposits can generally be placed into 4 major categories, which are termed orthomagmatic, hydrothermal, sedimentary, and weathering related. We will discuss each classification in detail momentarily. Orthomagmatic ore deposits are those that form due to the accumulation of minerals during the solidification of magmas. Hydrothermal ore deposits are those that form due to the accumulation of minerals from circulating fluids in the upper part of the Earth's crust. Sedimentary ore deposits are those that form due to the accumulation of minerals due to chemical and detrital sedimentary processes. And finally, weathering-related ore deposits are those that form due to an accumulation of minerals due to weathering. Orthomagmatic deposits are directly related to mantle plumes, or localized vertical columns of hot magma rising by convection in the mantle. Mineralization depends on the composition of the original milt and the evolution of the magma thereafter. Minerals from the magma are concentrated by processes which happen during cooling and crystallization. There are 3 processes which cause segregation of the minerals. 1. Liquid immiscibility, where the milt separates into 2 phases of different composition. 2. Gravity settling, where heavier crystals sink to the bottom of the magma chamber, accumulating in distinct layers. And 3. Filter pressing, where magmas enriched in heavier elements either accumulate into a solid floor of sunken crystals in the chamber itself or are squeezed out by filter pressing and form magmatic injection deposits. If additional pulses of magma are introduced into the magma chamber, the processes will repeat, forming an igneous layered ore body with rocks that may look similar to the specimen pictured on the screen. There are several ore deposits that can be generated from orthomagmatic processes, including chromite, nickel, copper, platinum, palladium, diamond, niobium, rare earth elements, ilmenite, iron, titanium, apatite, emerald, lithium, tantalum, and tin. Deposits are found in Australia, South Africa, Turkey, Russia, Canada, Siberia, Greenland, Norway, the United States, and India. In the interest of time, we will not highlight all of the orthomagmatic deposits, but I would like to touch on 2 I believe the viewers would find most interesting. Those 2 being orthomagmatic diamond deposits and an interesting mafic layered intrusion that was generated by impact forces from a large meteorite. Let's start with diamonds. Diamond ore deposits can fall into the orthomagmatic category. Kimberlite is an igneous rock which sometimes contains diamonds. Kimberlites cut through the country rock in vertical structures called pipes or dikes. Kimberlites can also form as an intrusive body that takes a more horizontal orientation called a sill. Kimberlites form deep in the mantle, about 90 to 280 miles deep to be specific, with lots of heat and pressure. This high pressure and temperature environment causes carbon atoms to strongly bond together, facilitating the growth of the highly sought-after diamond. Then, the kimberlite is erupted rapidly and violently up through the crust due to a large concentration of carbon dioxide gas in the magma chamber. Russia and the Democratic Republic of Congo are home to the world's largest diamond reserves, though deposits do occur in other countries such as Australia, Canada, India, and Indonesia. A couple diamond mines exist in the United States, but they are no longer active. One of the world's largest concentrations of magmatic nickel, copper, platinum, palladium, and gold is classified as an orthomagmatic ore deposit. The milt for this deposit in Sudbury, Canada, was generated from the impact of a meteorite that was 6 to 9 miles in diameter, which impacted Earth about 1.85 billion years ago. This deposit alone is the source for 1/3 of the world's nickel resources. The melted body of rock was produced almost instantly upon impact due to shock heating and then cooled. The melted body of rock is several kilometers deep and more than 60 kilometers across. The metals did not, however, come from the meteorite, but from the Earth's crust. Next up, the hydrothermal ore deposits. Hydrothermal deposits result from fluids put into motion by shallow magmatic intrusions in the upper part of the Earth's crust. The fluids have a magmatic component that may mix with meteoric water or seawater. These deposits are responsible for occurrences of copper, molybdenum, gold, silver, tungsten, tin, and several other minerals. In this video, we will briefly discuss the various hydrothermal ore deposit types, including porphyry, epithermal, sediment-hosted, Carlin, sediment-hosted stratiform copper, Mississippi Valley, volcanic massive sulfide, sedimentary exhalative or SEDEX, and metamorphic. Porphyry copper deposits account for over 70% of world copper production, making them an extremely important deposit type. They get their name from the porphyritic texture that is associated with shallow intrusions, which are the main host rocks. They typically form 2 to 4 kilometers below the surface from intrusions of magma that commonly feed volcanoes. The hydrothermal fluids that form porphyry copper deposits are largely made up of magmatic water that is lost from the magma through the process of hydraulic fracturing created by the intrusion itself. The fluids are highly acidic and attack or alter the rocks they move through, turning some of them into nothing but clay. Copper or copper-bearing minerals precipitate out of the solution at around 300 to 500 degrees Celsius due to cooling and changes in fluid composition. Mineralization is found as either disseminated, meaning spread throughout the rock, or concentrated in fractures surrounding the intrusion. The largest porphyry copper districts are located in the Andes, Central Asia, Western Canada, Indonesia, Chile, Arizona, and Mongolia. There are also several other porphyry copper deposits here in the western United States. Skarn deposits account for more than 70% of the world's tungsten production and are major sources of copper, iron, molybdenum, zinc, cobalt, gold, silver, lead, bismuth, tin, beryllium, rare earth elements, fluorine, and boron. Hydrothermal skarn deposits generally form in high-temperature environments related to zones of regional or contact metamorphism. Skarns can also form in shallow geothermal systems. As seen in the diagram, the zone of contact metamorphism would be proximal to the pink intrusive bodies in the immediate vicinity of the porphyry deposits. Hot hydrothermal fluids move through the surrounding rock, recrystallizing the rock, precipitating out a new suite of minerals, which can include valuable metals, nonmetals, and gems like garnet, ruby, and sapphire. Skarn deposits occur at several places around the world, including the United States, Canada, Australia, Russia, China, Africa, and Mexico, among others. Epithermal hydrothermal deposits account for 20% of gold production and most of the world's silver production. Epithermal deposits form at shallow depths proximal to volcanic activity in the upper parts of porphyry systems. The temperature of formation for epithermal deposits is low when compared to porphyry deposits. Fluids commonly discharge at the surface as liquids from hot springs and vapor from fumaroles in geothermal systems. These deposits form generally due to sharp temperature gradients at depths less than 1 kilometer. As the fluid ascends, pressure decreases, causing boiling, vapor loss, and cooling, resulting in the precipitation of gold and silica. The differing pH of the fluids accounts for the alteration patterns observed in epithermal deposits. Ore occurs in veins and disseminations in volcanic rocks and underlying rocks. Large epithermal deposits are found in Peru, the Dominican Republic, New Zealand, Japan, Bolivia, and Mexico. There are also several epithermal deposits in the western United States. Yellowstone would be an example of an active epithermal system. Carlin-type deposits are hydrothermal replacement bodies that are mainly hosted by carbonate-bearing sedimentary rocks. The ore fluid dissolves a large portion of the host rock and replaces it with gold, silver, and silica. The gold is commonly not visible without the assistance of a high-powered microscope. Carlin-type deposits are structurally and stratigraphically controlled and form at depths generally less than 2 kilometers and at temperatures largely less than 250 degrees Celsius. These deposits are broadly intrusion-related. Carlin-type deposits have only been found here in Nevada. If Nevada was its own gold-producing country, it would rank as the 5th largest producer in the world, and this is primarily due to the 100-plus Carlin-type deposits that fall along 2 major northwest linear trends in north-central Nevada. There are 2 main groups of sediment-hosted hydrothermal deposits. 1. Sediment-hosted stratiform copper deposits, and 2. Mississippi Valley-type deposits, which are grouped with clastic-dominated lead-zinc deposits. Sediment-hosted stratiform copper deposits are the second most important source of copper in the world and account for over 20% of world copper resources. The host rocks for these deposits are sedimentary rocks that form in marine basins of intracontinental rifts or passive margin settings. The ores follow sedimentary layers and consist mostly of copper-bearing minerals. The copper is thought to have been leached from underlying rocks and deposited higher up in the sedimentary sequence by circulating or migrating copper-rich basinal fluids as depicted by the blue arrows in the top diagram. The largest sediment-hosted stratiform copper deposits are found in Zambia, the Democratic Republic of Congo, Northern Europe, and Russia. Clastic-dominated lead-zinc deposits and Mississippi Valley-type deposits are the largest resources of lead and zinc in the world. Clastic-dominated lead-zinc deposit types are related to oxidation events that took place long ago in the geologic past, which changed fluid chemistry, allowing for mineral leaching by basinal brines from basinal rocks and later replacement and deposition below the seafloor during diagenesis, or conversion of sediment to rock. The ores themselves consist of thin laminations of sulfide minerals hosted in clastic sediments. Large deposits of clastic-dominated lead-zinc deposits occur in Australia, Canada, and Alaska. Mississippi Valley-type deposits, also referred to as MVT deposits, consist of concentrations of the minerals galena and sphalerite with locally abundant fluorite and/or barite. MVTs formed as replacement and open space filling of mostly carbonate host rocks long after the rocks were deposited in a foreland basin, which is a structural basin that develops adjacent and parallel to a mountain belt. Continental scale brine migration from the deeper to shallower parts of the basin is caused by collision-driven uplift. The largest MVT deposits are found in Poland, East Tennessee, and other locations of the eastern U.S. Now we will dive down into volcanic massive sulfide deposits, or VMS deposits. VMS deposits form in volcanic environments at shallow depths below the seafloor in the oceanic crust. VMS deposits are known to host occurrences of copper, lead, and zinc. Seawater penetrates deep into the oceanic crust where it is heated by underlying intrusions. Seawater may mix with magmatic fluids that are already enriched in metals, or the fluid may leach the metals from the oceanic crust through which they move. Metals are later precipitated due to cooling and other processes below the seafloor, replacing subsurface rocks. Black or white smokers represent the surface counterparts to VMS deposits and occur as vents on the seafloor. When the hot fluids vent onto the seafloor, they mix with cold seawater, and the sharp temperature decrease and change in composition cause the rest of the metals that weren't deposited below the surface to fall out of solution. The sediments may form chimneys on the seafloor and settle or accumulate like blankets around the chimney. Metallic deposits that form around the vent or in more distal locations on the seafloor are also referred to as SEDX deposits. Most VMS deposits are relatively small, but this is not always the case. Large VMS deposits are found in Canada, Europe, Spain, and Portugal. The final type of hydrothermal ore deposits we will discuss are metamorphic hydrothermal deposits. Remember, metamorphism happens when a rock is exposed to heat, pressure, or chemically activated fluids. Very few economic deposits are formed directly from metamorphic recrystallization alone, though asbestos, garnet, graphite, talc, uranium, ruby, emerald, and sapphire can form due to this process. However, fluids generated during metamorphism do result in economic deposits, but because circulating fluids are produced, these deposits fall under the hydrothermal category. Orogenic is a term used when talking about the geologic process of mountain building. During orogenic processes, rocks are exposed to lots of heat and pressure. Prograde or post-peak metamorphic processes can release a large amount of fluid. Many orogenic gold deposits are related to dewatering events in just these kinds of environments. Orogenic gold deposits are responsible for about 1/2 of global gold production. Orogenic gold deposits consist largely of quartz and gold veins that are hosted by deep crustal fault or shear zones. Gold was likely derived from volcanic and sedimentary rock sequences, and possibly in part from marine pyrite, then concentrated due to chemical reactions with the surrounding wall rocks. Large orogenic gold deposits are located in Ghana, Australia, Canada, and the U.S. The well-known California Mother Lode is an example of a hydrothermal metamorphic gold deposit. Now we will move on to deposits that fall into the sedimentary category. The first sedimentary deposit type we will discuss are placer deposits. The most well-known type of placer deposit is placer gold. This is the type of deposit that fueled the gold rushes to California, the Yukon, and to Australia. Less than 20% of the world's gold is obtained from placer gold deposits. Placer deposits occur when an ore body is eroded and valuable minerals within accumulate due to gravity separation during sedimentary processes. In this deposit type, the ore is mined from gravels created in streams and rivers. Gold occurs in native elemental forms and is deposited in areas of the stream or river where the current is weak and can no longer keep the gold in suspension. Large placer and old or ancient paleoplacer gold deposits are found in Witwatersrand in South Africa and Canada. Ore from Witwatersrand is shown in the photo on the screen. Other minerals that can occur as placer deposits include diamonds, rubies, sapphires, and alloys of platinum group minerals because they are hard and resistant to weathering. Beach sands can have high concentrations of detrital or heavy minerals such as ilmenite and rutile and are also a major source of the high technology metals titanium and zirconium. The next type of sedimentary ore deposits we will discuss is banded iron formations. Banded iron formations, or BIFs, are the main source of iron globally. BIFs consist of alternating beds of chert and iron-bearing minerals which include magnetite, siderite, hematite, and/or iron silicates. These deposits can be several hundreds of meters thick and extend laterally for several hundred kilometers. BIFs mark the introduction of oxygen into the Earth's oceans during the Precambrian. After the evolution of photosynthetic cyanobacteria, free oxygen was released into the oxygen-poor oceanic waters, which reacted with the dissolved iron in the water and precipitated these iron-rich layers of rock. The largest BIF deposits are located in Brazil, Canada, Western Australia, South Africa, the Ukraine, and Michigan in the United States. Moving on to sedimentary depositional deposits. In some geologic environments like a closed basin or an isolated body of water that receives minimal influx of outside water sources, the water will naturally evaporate and become supersaturated in particular elements. Minerals will begin to form depending on the composition of the fluid and precipitate out of solution, making sedimentary layers of ore. Salt, gypsum, borax, barite, anhydrite, manganese, phosphates, silica, and some varieties of limestone and dolomite are some examples of minerals or rock formed by this process. These layers may repeat, indicating a cyclical input of water followed by evaporation, supersaturation, and mineral precipitation. Sedimentary deposits can be found in several regions of the world, including the United States. The United States is the leading producer for phosphates in the world, which are primarily used as agricultural fertilizers. The final group of mineral deposits we will discuss are the surficial mineral deposits. The first type of surficial deposit we will review are laterites. Laterites are where most of the world's bauxite comes from. Bauxite is the primary source of aluminum, like that used to make aluminum foil. In hot and humid tropical regions, especially those with distinct wet and dry seasons, some metals are concentrated in laterites, a type of soil in which most elements have been leached, leaving only those elements that are immobile during weathering. Different rock types will produce different concentrations of minerals when leached, including bauxite from granitic rocks and nickel and cobalt from ultramafic rocks. Certain specialty clays also form in these types of environments. Large laterite deposits are located in Australia, the Caribbean, Africa, and South America. Gold may also occur in laterite deposits, some which are located in Brazil, Western Africa, and Western Australia. The second type of ore deposit in the surficial group is termed supergene enrichment. Again, this is a concentration of minerals due to weathering. Metallic deposits exposed at the surface undergo weathering that releases metals into the groundwater. These metals consist mostly of copper, lead, zinc, and silver. They can then precipitate out of solution to create supergene-enriched deposits. Iron and sulfur oxidizing bacteria above the water table cause leaching of copper. The copper is transferred downwards into a reducing environment which causes the copper-bearing minerals to precipitate. This process can produce a metal-rich zone or blanket with copper concentrations up to 2 to 3 times greater than the underlying ore, and makes an ore zone that is more easily extracted. To summarize, Ore deposits generally fall into four main groups: orthomagmatic, hydrothermal, sedimentary, and weathering-related ore deposits. Each group has several ore deposit types within, each with a common environment of formation and ore fluid evolution. Each deposit type produces specific accumulations of minerals that can be found only in the correct geologic environment in particular parts of the world, but collectively contribute to the growing global demand for resources. Well, we have covered a lot, but I hope that after watching this video you walk away knowing more about the many types of ore deposits and the environments in which they form. We use minerals every day, and some are even used all day long. From cars, solar panels, electrical transmission, and geothermal wells to cell phones and the device you are listening to right now, minerals make it all possible. Understanding where and how to find mineral deposits allows modern prospectors to find new deposits needed to provide the necessary commodities to sustain modern-day living around the world. And as we have learned, there is a lot to understand. I would like to thank you for watching this video summarizing ore deposits, and have a great day.